Alright, good morning class. Today is Monday, March 23rd, 2020, and this is going to be today's video lesson for lesson number 12. Today we're going to be talking all about non-visible light, the light that you cannot see. We'll explain everything that means in just a minute. It's going to be a very exciting lesson today, I think. But before we get into that, I do want to recap. I want to kind of get everybody on the same page, catch everyone up to speed. There were a few folks who just this weekend kind of got their computer access, got caught up with some lessons. And then for the rest of you who were doing your lessons last week, it's been 3 or 4 days since you talked about light, so I want to make sure that we're all back on the same page. I want to review all the lessons from this unit, all the way starting back at lessons 1 through 8 when we were talking about energy in this unit on energy and light. Now, we learned a whole bunch of stuff in our lessons about energy. We did a whole lot of math and calculations, but one of the very big ideas that we learned that's going to be important for today is this basic idea that energy comes in a whole bunch of different types or different forms and can convert, that's that word that we used, from one type into another. We learned that there's a whole bunch of types of potential energy out there in the world and a whole bunch of types of kinetic energy to boot. And we learned that light, which we're talking about now, is one type of kinetic energy. Today we're going to be seeing some experiments in which light energy is being converted to other types, and so that's an important thing to recognize going in, is that it is a type of energy, and yes, all these types of energy can convert into all of the other types. Now, in lesson 9, we started introducing light as a concept. We talked about the fact that light is a form of energy, and it travels incredibly fast. That was one of these things that we also said. Light doesn't just appear in a room and it's there all of a sudden. Instead, it's always going from one place to another in the form of a wave, and it's traveling all the time. We said that if you had a spaceship the speed of light, it could go around the Earth 7.5 times in 1 second. That's how fast this animation is going. And that, yes, light travels in this form that we call a wave. In lesson 10, we went into a little bit more depth on that by specifically looking at lasers, these kind of guys that we see up here. We saw a diagram that looked like this. I want us to be very clear on the big ideas we took away from lesson 10. Those big ideas were, heading into today, first of all, that lasers are a simple or a pure type of light that only sort of operate with one wavelength at a time. They're exactly one color. Second of all, that light is made up of waves, that it travels in this wave-like fashion where it goes forward, but while it's going forward, it's kind of waving up and down the whole time. We learned that a laser's color depends on its wavelength, so the difference between these violet lasers up here and these red lasers down here is their wavelength, the distance from the top of one crest to the top of the next crest, or how kind of stretched out the waves are. They're longer down here with the red light, and they're shorter up here with the violet light, and then they're in between for all the other colors. And we learned that how the wavelength affects not only the color of light, but also the amount of energy it has. So we have more energy the shorter the wavelength gets. So of all these colors here, violet has the most energy and red has the least energy. That's because violet has the shortest wavelength and red has the longest wavelength. And the shorter your wavelength is, the more energy that color of light has. Now, the very last lesson that we had was lesson 11, where we learned about white light. On this lesson, the big ideas we took away were two main things. First of all, we saw our guy Styropyro do this little experiment where he combined 3 different lasers of different colors and used them to produce a white laser. And we saw that that's the color that gets created when these 3 colors, red, green, and blue, combine. We learned that normal white light that's all around us all the time is actually made up of all the colored wavelengths combined. So there are no white light rays, there's just different colors of light rays, and when they combine, they happen to make the color white, the normal white light that we see all the time. Second of all, we learned that doing the opposite of this, where you combine different colors and you make white, is doing this over here with the prism, where you start out with white light, and you pull it apart into all of the separate colors. We learned that a prism, that's that word, can pull white light apart into all the colors that make it up, and that's what you can see happening in this diagram. White light is going in, and this prism is separating out all these different colors of light with all their different wavelengths. So by the time it's coming out of them, it's kind of making almost a rainbow, and that is in fact how rainbows work. Now, while we were doing that, I do want to shout out a few people who had absolutely exemplary notes. That means notes so good that I want to show them off to the rest of the students and show you how good they should look. I had a whole bunch of people from the last lesson send me in notes. That included Robert down here. That included Layla, also from Purdue. We had Sinclair sending in notes from UT. We had Vicky sending in notes. We had Caden sending in notes. And I think we had one Georgia Tech student. Yes, we had Tashia also sent in her notes. Across all these different notes, we were seeing various key ideas, we're seeing questions being answered, we're seeing diagrams being drawn, and all these students are getting dollars added to their paychecks for not only taking such good notes, but sending them into Mr. Manta. Again, if you want me to show your notes off to the rest of the class, go ahead and take a picture and get them emailed to me. Right now, it looks like UT is in the lead. I had 3 different students from UT all sending in good notes. Purdue, Georgia Tech, we got to catch up. All right. Today, I want us to start out, now that we've kind of recapped some of that material, with the do now. So, open up your notebooks. You only need to answer these questions in your science notebook. You don't have to put them online anywhere. This is just for you to quiz yourself, make sure that we're all on the same page. You have 5 questions right here, and then there's going to be, I want to say 4 more. But first, I'm going to instruct you. Take out your notebook, number it 1, 2, 3, 4, 5. Pause the video and answer these questions now. You don't need to write complete sentences, but you do need to actually write out your answers. For example, what you would say here and here, whether you would pick a blue laser or red, all of those. Pause the video, do that now. Alright, you should be unpausing. Hopefully you've answered those 5 questions. Before I give the answers, we actually have 4 more questions. Pause the video, copy this diagram of a light wave into your notebook, and use it to answer 6, 7, 8, and 9, labeling those 4 things. Pause the video and do that now. Alright, unpausing the video, we're going to go ahead and start going back through the answers. You should have answers to all 9 questions written in your notebook already, so you can genuinely say by the end of this whether you got them right or wrong before I show the answers. Now, number 1. Tony plays a baseball game on a hot summer day and feels the light from the sun warming up his hat. This is an example of light energy converting to thermal energy. Feeling his hat warm up means his hat is getting hotter, it is gaining heat or thermal energy. So we have light energy, and again the word is converting to thermal energy. Question 2 is asking which has a longer wavelength, a blue laser beam or a red laser beam. Well, if we think back to the kind of rainbow diagrams that we've been seeing of our wavelengths, we can see that blue is up here. It's got a pretty short wavelength, all things considered, and we're comparing that, I want to say, to, what did it say? A red laser beam that actually has the longest wavelength. So when this question is asking us which has a longer wavelength, the blue or a red laser beam, it is definitely going to be the red, because red we can see has the longest wavelength of all the different colors. Question 3 is asking which has more energy, a green laser beam or an orange laser beam. Now, this isn't wavelength. This question is asking about energy. So you have to know 2 things here. We have to know, first of all, that energy goes up the shorter our wavelengths are, and we have to know which of those 2 colors has a shorter wavelength and therefore more energy. So let's see again. Green or orange? Well, I can see that green has a pretty short wavelength here. Orange is a longer wavelength. Since green is shorter, that means green has more energy than orange because it has a shorter wavelength. Number 2 was red, number 3 was green. Number 4, true or false? Just like orange light is made up of orange light waves, white light is made up of white light waves. Well, we saw the other day that if you were to zoom into white light, look super close at it, you would not see a whole bunch of white light waves. There's no such thing, the same way that there are for the colors. Instead of white light, when we zoom in super close, we see this is made up of all the different colors combined. So this one is going to be false. And 5 is asking what tool can you use to pull white light apart into the colors that make it up. We learned that that tool is called a prism, that triangle looking thing that can turn white light into a rainbow by pulling the light apart. Alright, for 6, 7, 8, and 9, I'm gonna copy these answers right on my diagram right here. First of all, we were supposed to label a crest. Your crest could have been this one, or this one. A crest is the same thing as a peak. That's just a high point on the light wave, the very top point. The opposite of that is a trough. Your trough could have been right here or right here. That is the low point on the wave or the diagram. I mean, technically, if you want to be very specific, it's like only this exact point right there, but whatever. We have 2 troughs, we have 3 crests up top. 8, we were asked to label the amplitude. Your amplitude is the distance from the midline right here up to the very peak of a crest, like that. So this right here could be your amplitude. You also could have labeled it right here or right here, and it's the same. Actually, you could, if you wanted to, label it going down to a trough instead. That or that would all be amplitude. And lastly, number 9 was asking to label the wavelength. The wavelength is the distance in between 2 crests or 2 troughs. So the easiest one would be to say from here straight to here is 1 wavelength. You also could have done from here to here or from here to here. Each of those would be an example of a wavelength. Okay, so we saw our answers for 1 through 5. We saw our answers through 6 through 9. Question 1, classwork question 1 now, to go in the Google form and write this down, is simply to tell me how many out of the 9 did you get right on today's Do Now. Give me an honest answer. It's not being graded. I'm just trying to get a sense of how well students are understanding this material. Just give me a number 1 through 9. Pause the video and do that now. And we're going to keep on moving on. All right, so we could finally jump into some new material for today. And for today's lesson, ladies and gentlemen, we are going to step back in time, all the way back to the year of 1800. Now, in 1800, a typical home, especially in somewhere like Victorian England, which is where we're going to be, might look something like this. Looks pretty darn old, doesn't it? It wouldn't be in black and white if you're really there, of course. It's just the camera could only capture black and white. And we're going to step back to the year 1800 because we're going to talk about the early science experiments that discovered non-visible light, which is today's topic that we're talking about. Back in the year 1800, there were these two scientists, these two guys. The first one was this fella right here named William Herschel. William Herschel was a very famous scientist at the time. He was considered the King's Royal Astronomer in England. He was mostly credited and he was very famous for discovering the planet Uranus. He was a very big deal back then. He was a very decorated scientist, and he made an important discovery about light that we'll talk about in just a second. And there was this other scientist that we need to know about, who wasn't that famous back then, who isn't that famous today. You can tell he wasn't that famous because he didn't have a proper portrait made. The best portrait that exists of him is these kind of silly little drawings. But he was equally important, a guy named Johann Ritter. He was also a scientist working in the year 1800. These two guys knew each other, and they kind of worked together, but Herschel was a heck of a lot more famous, considered more important than Ritter. But the two of them together made a really important discovery that they both deserve credit for, which is what we're going to be talking about today. Well, what was their discovery? Well, let's see what the experiment was that they ran. First of all, we're going to start with Herschel. Herschel one day was messing around with prisms, and now we know what a prism is. We learned about them in our last lesson, and by the year 1800, people had already discovered, mostly Isaac Newton had discovered, that if you shoot a beam of white light into a prism, it would separate it out into all of these separate wavelengths, and it would make a rainbow. There are also some people had done an experiment to see which of the different colors in the rainbow had the most energy, and so Herschel was just trying to kind of redo that experiment. The way he tried to figure out how much energy does each of these colors in the rainbow have is by using a thermometer. What he did is he took his thermometer and he stuck it into each one of these different colors in the rainbow. First he put it in the purple part of the rainbow, and he saw his thermometer shoot up super high. Why was that? Well, that was because we know that light energy can convert to thermal energy, and when he had his thermometer in this beam of purple light and all the light was hitting the thermometer, well, the same way that sunlight makes you feel warm, that purple light, which has a lot of energy, because we know purple light has a really short wavelength, started heating up the thermometer, making the thermometer go up. So the hotter the thermometer got, the more energy he could tell was in that particular color of light coming out of this prism, coming through this rainbow. So first he put the thermometer in the purple, saw that it gained a whole bunch of energy. Then he moved his thermometer to the blue, and he saw that when he put in the blue light, it still had a lot of energy, but a little bit less than a purple. Then he moved it into the green light, and he saw that it gained a little bit less energy. And then he moved into the yellow light, and he saw that it gained a little bit less energy. And then the orange had a little bit less energy. And then the red light had the least energy yet. It barely made the thermometer move at all. Now this makes sense to us because we already learned that red light here has the least amount of energy in the rainbow because it has the longest wavelength compared to violet light, which has the shortest wavelength. So far, Herschel hadn't really discovered anything. He just replicated some experiment that someone else had done, showing us that red light has less energy than violet light. But what happened next was really interesting. Herschel kept moving the thermometer. He decided to move the thermometer into the empty space past the red light, just past here where there was no light beam whatsoever. It's just empty black space where no light was passing. And to his amazement, in that spot, the thermometer got hotter than it ever had before. The temperature in this spot, in this empty blank space, went even higher than it had gone in the violet light. And the violet light, we know, usually has the most amount of energy. So it was almost like there was some kind of invisible light coming out of the prism in this extra space past the red light that was hitting the thermometer and making it get hot. That was really strange to him, because how can you have invisible light that's still warming up a thermometer? He had never seen anything like this. Well, Herschel wrote a paper about this discovery that he had made, and he started sending it to all the other different famous scientists at the time. And one of the people who found this paper and heard about this very strange discovery was this guy, Johann Ritter. Mr. Ritter decided to do kind of a follow-up experiment, the same idea as what Herschel had done, but instead of using a thermometer, he used a very special chemical. He made a test tube of this special chemical, I believe called silver chloride, and he knew it was a special chemical because when you exposed this chemical, silver chloride, to light, it would go through a chemical reaction, and it would change color. In this case, you have light energy converting into chemical energy, and we've learned that that's an energy conversion that can happen. He did a similar experiment to what Herschel had done, but found a slightly different result. So first, he took his chemical and he put it in the red light, and he saw that produced a pretty small chemical reaction because red light doesn't have that much energy. Then he moved it into the orange light, and that made a little bit of a bigger chemical reaction. Put it in the yellow light, and that made a little bit bigger of a chemical reaction. He put it in the green light, and that got even bigger. The blue light, that got even bigger, and he put it in the violet light, and he got the biggest chemical reaction yet of all this chemical called silver chloride reacting and changing color because it was absorbing all of this light energy. But then he noticed something strange as well. He took the chemical and moved it down past the purple light into the blank space where there wasn't anything at all, and he got the biggest reaction yet. Again, it was kind of like what Herschel had found. Even in this empty space where no light seemed to be passing through, it was almost like there was an invisible kind of light that was hitting his chemicals and making them react. On this side, past the violet light, just like Herschel had found, almost like there was some kind of invisible light up here past the red. What these two guys worked out by talking to each other and working out with some other scientists was that they had made an amazing discovery. Their discovery was that there are wavelengths of light which human eyes can't see. If we look at our diagram over here, you notice that the wavelengths, as we go from red to violet, go down from 665 nanometers, 630, all the way down to 400 nanometers. Well, 400 isn't zero. There's no reason why you couldn't, in theory, have light with an even more narrow wavelength. I'm sorry, that's a terrible drawing. A more narrow wavelength than the violet light, right? That gets even shorter and shorter and shorter. Herschel and Ritter discovered that the spectrum of light that goes from red to purple keeps going. That there are wavelengths of light shorter than violet light, and the reason we don't see them is just because the human eye literally can't see them. But in their experiments, they were able to detect the invisible light that's on this end of the rainbow and the invisible light that's on that end of the rainbow. There are colors of light that human eyes cannot see. So this whole spectrum right here, it doesn't end with violet at the top and red at the bottom. In fact, it keeps going, and there are more and more colors that we just can't see that are even more violet than violet and even more red than red. It goes this way too. There's a bunch of light that we can't see because our eyes are only made to detect light of this wavelength in between purple and red. There's more light that keeps on going down here and that keeps on going up here, but we just literally cannot see it. We call all of this light, the stuff that we can't see, non-visible light, which literally just means not visible. We can't see it, but it's there, and it behaves just like all of the light that we can see, just the same, but we can't see it. Alright, class for question 2. Pausing just to quickly check if we understand. We should be filling this question out in the Google form. True or false? People can see all of the light that there is. Pause the video, answer that now. And bringing it back, you should have answered that question in today's classwork. You should know that the correct answer is false. As we just said, people can't see all of the light that there is. There's more wavelengths of light this way and this way that's beyond what our eyes are able to see. And today, we're going to learn about them. So, if you want to learn just how much light there is, oh yeah, answer false. I got the order all goofed up. There are wavelengths of light that we can't see if we go this way, or if we go this way. There's more light, our eyes just can't see it. Here's the really mind-blowing part for today. not only is there some kind of light that we can't see, there is in fact way more non-visible light than visible light. As in, most of the light, most of the kinds of wavelengths that are out there, our eyes can't see. We're actually missing most light. Most light is invisible to us just because our eyes can't see it, but it's still there. People have figured out ways to detect it and ways to actually use it in technology and engineering. And we're going to learn about some of those types of light today. Well, how much other light is there? Well, let's take this as an example. I'm going to take this diagram that we've seen a few times now that goes through all the visible light, all the colors of the rainbow that we can see, from red up through violet. I'm going to take it, turn it on its side, and I'm going to shrink it down really small and put it on what is really the true rainbow, or really we would say the true spectrum of all of the kinds of light that exists. And we can see, when we look at the full range of wavelengths, that the visible light that our eyes are made to see is just a tiny little part, a tiny fraction, a tiny sliver of all of the wavelengths of light that really exist that we can't see. So all this stuff over here we can't see, all this stuff over here we can't see, only this tiny little bit in the middle is what we can see. That bit right there contains all the colors of the rainbow, red through purple, every color that we could imagine. And that is the visible spectrum. All the rest of this stuff is what we call, again, non-visible. What we're going to get a chance to do for the rest of today's lesson is learn a little bit about each of these kinds of non-visible light: radio waves, infrared, ultraviolet, X-rays, and gamma rays. We're going to go one by one. We're going to kind of like start in the middle and go this way first, and then come back and go this way at the end, if that makes sense. Just taking these groups one by one. First of all, let's learn a little bit something about infrared light. Infrared, there's an R there. Don't say infrared, it's infrared. Infrared waves are the kind of light that their wavelength is just a little bit longer than red. So it's like, it's extra red almost. So red that we can't see it. You can think of it that way if you want to. Infrared is interesting because it's related to heat. Anything that's hot emits infrared light to get rid of its heat. It radiates away infrared light. So it's almost, in some ways, people think of it as almost like synonymous with heat. You can't quite say it that way, but that's the basic idea. One thing that's really cool is that even though human eyes can only see this bit of light that's right here, some animals, like snakes and certain insects, can actually see infrared light. It's almost like they can see colors of the rainbow that we can't even imagine. Snakes and insects can see it and that helps them hunt, because, for example, snakes are usually hunting warm-blooded creatures at night, and they can see their heat, because infrared, anything that's hot puts off infrared light, because they can see infrared light. Their eyes are made to see that, and our eyes aren't made to see that way. Another cool thing is that people, even though our eyes can't see infrared light, we have invented things like thermal cameras or night vision goggles that we can use to then see infrared light. For example, this fella right here, what you're seeing right here is a picture, the same picture side by side, except this is a picture taken with a normal camera looking at visible light, and this is a picture taken with a thermal camera. It's a camera that sees heat by using infrared light. And you can see that this guy's skin is the hottest part of his body. It really lights up. And you can even see his hands through this black bag because the heat from his hands is radiating through the plastic. This is a picture taken with a thermal camera where the camera can see infrared light, even though our eyes can't see infrared light. You might have also seen pictures of soldiers in the army who wear, here I'll point to these kind of crazy looking goggles on their head, and they can walk around at night and everything looks kind of green. That's because they have these special goggles that can pick up infrared light, which allows them to see kinds of light that human eyes normally can't see. And that way they can see at night, which is pretty cool. Alright, if we take another step over from infrared light, we get to the very longest kind of light, or longest wavelengths of light of all. These are radio waves, the longest of all. When I say long, I mean they have a really long wavelength, kind of like that. So they're not all bunched up tight. They have a really long sloping wavelength. They're really stretched out. Radio waves are the longest wavelength. When I say radio waves, yes, I am referring to the radio, like the kind of radio that you can listen to in your car. The way the radio in your car works is that, we'll explain that in just a second, is that you are actually picking up with your car's antenna certain wavelengths of light that are bouncing around in the air. Radio waves can travel super far, so it's almost like a light that can just travel extra far. It can bounce across things. And when you tune your car radio to a certain station, like if you turn it to 104.3 FM or 97.9 FM, the radio station, what you're telling your radio to do is look for light of that particular wavelength. You're saying, hey, instead of looking for yellow light or for purple light, look for light that is of the wavelength equal to 104.3 hertz, which is another way that you can measure, not wavelength, but frequency, but the same kind of idea. So your car, like even though your eyes can't see the light that's over here, your car antenna can, and it can pick up that light and use it to get a radio signal, which is really cool. This is an interesting little diagram of how radio works. It's a really complicated technology. It's a whole thing you could study at college if you wanted to. But basically there are radio towers all around the city, and if they want to send radio information to your cars, you can listen to music. They bounce radio waves sometimes off of the atmosphere or off of the ground, and then they end up going to people's cars or the other radio stations and transmitting around. It's really interesting. All right, now, if we come back, so radio waves were the longest wavelength of light, all the way on this far left side. Now, if we come back to the visible spectrum in the middle, and we take one quick step to the right, we can say what's just a little bit shorter than violet light. We get to this kind of light called ultraviolet. Ultraviolet waves have a shorter wavelength than violet light, so they're even more purple than purple, is a way that you could think about it if you wanted to. Ultraviolet is often abbreviated to just UV, ultraviolet. UV light is emitted by the sun and special types of lamps. I'll show you an example of that in just a moment. And again, many animals, including insects, birds, and some scientists are now even saying cats and dogs can see ultraviolet light. Again, this is almost like these other animals can see colors that we can't even imagine because they're off the end of the rainbow of what we can actually see. Interesting thing to know about UV light. UV light that comes from the sun, because the sun does produce ultraviolet light, can cause sunburns. The way that sunscreen works is that it's made to block or reflect ultraviolet light. So all the other kinds of light can pass through, but ultraviolet light bounces off of sunscreen if you put it on your skin. So a couple things to show, interesting pictures I want to show here. First of all, this is a light that you can buy on the internet that's made for growing plants in your house. And it emits some amount of normal violet light, that's why the picture is kind of pink, but also a whole bunch of UV ultraviolet light, because the sun emits ultraviolet light and plants actually really like to absorb ultraviolet light. It can help them grow. Second thing to know, this picture is kind of funny. This is what I was talking about sunscreen a second ago. If you look at this picture, what's happened, which is really interesting, is that this guy had some of his friends come along with a bottle of sunscreen and draw a smiley face, sun, on his back out of that sunscreen. You can kind of see it if you look close enough. And then what they did is they had him stand out in the sun, and they took a picture of him on this side with a camera that can see ultraviolet light. And what you can see is that when they use that camera, you can see that smiley face really clearly that was drawn with sunscreen, because sunscreen is made to block ultraviolet light. And the camera used for this picture is taking a picture of ultraviolet light, whereas this one is taking a picture of visible light. That's why you can see the smiley face here, but you can't really see it so much here because it's made of sunscreen, and sunscreen works with ultraviolet light. That's what UV is all about. If we take another step over from ultraviolet light, we get to X-rays. X-rays they have an even shorter wavelength than ultraviolet light does, and you've heard of X-rays before, you know how these work. X-rays can pass through our skin and our muscles, but not our bones, and that's why they're useful and they're used in doctors' offices. Quick thing to note, because some people get nervous about it, and I just want to point this out. X-rays can be bad for your health in high doses. That means like if you get hit with a bunch of X-rays all at once, but the amount that they use at the doctor's office is not high enough to cause problems, any kind of health problems for anybody. It's only if you got like 1 million X-rays every single day for the whole year that it might be dangerous for your health. These are some pictures of X-rays that you might have seen before. So what's going on here is that they've taken pictures with a camera that can detect X-rays, and they've shined X-rays through these various body parts, like someone's shoulder and someone's hand and someone's knee. And the rays are able to pass through little spots like here and here and here where it's just skin and muscle, but they can't pass through the bones. So when the X-rays try to pass through the bones, they get blocked. And that's how you end up with a picture of someone's bones or someone's skeleton going on inside of their bodies, because X-rays can pass right through skin and flesh just fine, but if they try to pass through bone, they get blocked. They hit it, and they can't pass through anymore. We can use those then to make x-rays and help people figure out what's going on with their injuries. And lastly, final type of light that we need to know about are these things called gamma rays. Gamma rays have the shortest wavelength of all. They're all the way over. So here's the here's the visible spectrum here. The shorter wavelengths than that are called ultraviolet. Even shorter than that are X-rays. And the shortest wavelength of all are gamma rays. Now, we've already learned that the shorter a wavelength is, usually the more energy a type of light has. And so as you might guess, yes, gamma rays are super high energy because they have the shortest wavelength. This makes gamma rays pretty dangerous, but they're also pretty rare. You probably don't have to worry about any gamma rays anytime soon. Gamma rays mostly come from nuclear bombs and radioactive waste, and they're one of the reasons that nuclear bombs and radioactive waste are so dangerous to be around, and why you hear about people wanting to avoid those things for the most part. So, there's a picture of a nuclear bomb, and there's a picture of radioactive waste. Those are pretty much the only two instances where you would be likely to detect any gamma rays coming out from anything that would be any harm to you. So unless you plan on hanging out with some radioactive waste anytime soon, you don't need to be worried about gamma rays. You're probably not going to find any of them anywhere. Alright, that was a whole bunch of information, right? Learning about all these different types of waves all along this whole spectrum. Just to recap the way that this all works and to make sure that we get our words right, I want to be very clear. When we're looking at this whole big diagram known as the spectrum of light, only this tiny middle section is the rainbow that we can see. Red, blue, orange, yellow, whatever. The colors that we can see. And that is termed visible light. That just means, hey, we can see it. Everything else, all this stuff over here, as well as all this stuff over here, instead gets called non-visible light. That means that it's light that is not visible to us, either because the wavelengths are too long, in this case, or they're too short, in this case. And our eyes are only made to see this much of the light, but all this other light is bouncing around us all the time. Just to be extra clear, all of it together can be called light. So even though you can't see radio waves, they are a kind of light. Even though you can't see X-rays, they are a kind of light. And the last thing that I want to add is that there's a fancy science word that scientists use sometimes instead of light when they're talking about all these different kinds of light, and that term is electromagnetic radiation. It's a big fancy word, I mean 2 words really, and it just means the exact same thing as light. It's just sometimes you'll hear scientists talking about, X-rays as electromagnetic radiation, and that's just a fancy way of saying light. You might sometimes hear Mr. Manta talking about different kinds of electromagnetic radiation. All that means is it's different kinds of light. 2 different words that mean the same thing. Now, you might be thinking, what this woman, I think that's Chrissy Teigen? I don't know. Who knows? I might be way off there. You might be thinking, Mr. Manta, how much of this do I have to know? I just told you a whole bunch of information about all these different types of light. I know X-rays, all this kind of stuff. So how much do we really have to know? And I want to be clear with you that you have to know all of it. Every single thing that I just said could... No, I'm kidding, of course. I'm just kidding. You don't have to know all of it. That would be way too much information. Instead, here's what you should know from today's lesson. Here's what you need to take away. First of all, you should understand this diagram. If I ever show you this diagram, you should understand kind of what you're looking at and the difference between visible and non-visible light. The central idea being that we can only see this tiny little bit of the spectrum of the kinds of light that exist, and all the other types are considered non-visible. Second of all, you should be able to put the different kinds of light in order, from longest to shortest. So you should know that radio waves are longer than infrared, infrared is longer than visible light, visible light is longer than ultraviolet light, which is longer than X-rays, and that gamma rays are the shortest of all. You should kind of know this order, like 1, 2, 3, 4, 5, 6. Man, it's very hard to write on this right now. And know the order that they come in. And third of all, if I give you a fun fact, like all that information we just learned about all the different types, about a type of light, you should be able to identify which type I'm talking about. So for example, if I say this kind of light can shine through your skin, but it can't go through your bones, and so doctors use it at the doctor's office, you should know that I'm talking about X-rays. If I say this is the longest, this kind of light has really, really long wavelengths, and we use it to broadcast radio stations to your car, you should know I'm talking about radio waves. If I say this kind of light has a long wavelength but not a super long wavelength, and it's related to heat, and some kind of animals like snakes can see this kind of light, you should know that we were talking about infrared light. Different examples like that. You'll have a question kind of like that on your exit ticket today. That's what you need to know. 1, 2, and 3. All right. Taking that away, it is all that we got for today, and it is now exit ticket time. You can go ahead and close out the video, and yes, as a heads up, you do have some independent work as well for today. That, as well as the exit ticket, are due by 6 p.m. I also want to mention today's cool thing. I'll try to link it somewhere if I can, but if not, go ahead and search it on YouTube. Since we were talking about this picture of the spectrum of light, there's a very famous album, a selection of music by a band called Pink Floyd that uses this picture of the light spectrum of a prism as their album art, as kind of like the front cover of the album. It's an album called Dark Side of the Moon, and it is today's cool thing. It's by a band called Pink Floyd again. Today's cool thing because it's maybe Mr. Manta's favorite album of all time. I started to listen to this kind of music when I was right around your guys' age, and it absolutely blew my mind. If you are bored, you have some downtime today, and you like music, go search on YouTube or Spotify or whatever the album Dark Side of the Moon by Pink Floyd and give it a good, proper listen. It's amazing. It's so good that you can even sometimes find silly YouTube videos of people doing these reaction videos where like they listen to it for the first time and they are in tears by the end of it because it's a freaking great rock album. All right, that's all that we got for today. Just want to show you one more time. If we come to today's classwork, you'll have the video lesson, the classwork which you just did, the exit ticket which you should do now, and then a reading and some questions for your independent work today that are tied to each other. All right, that's all we got for today. Take care, folks. Have a good one.